So there's one other additional time when you can have an acidic salt. Soluble salts with small, highly charged cations. So cations like aluminum 3 plus and iron 3 plus have enough charge to bind strongly to water molecules. It's small, so you've got a high, large coulombic, they're small and they have very large charge. And so therefore the water molecules can get pretty close and are strongly attracted by charged dipole interactions. And so what you get when you dissolve Al3 plus in water is it actually complexes with 6 waters to produce something, a complex we'd write out as Al, H2O, 6 of those, 3 plus. And then what can happen, and this is probably easier if I show the picture here, this is what the complex looks like in solution. You have waters sticking on the sides in an octahedral geometry. But because the iron is pulling so hard in the oxygen, it's pulling electrons away from those water molecules. And so the hydrogens are really easy to pull off. So once you have this, which is mostly, this is the dominant species here, what you get is then when it interacts with water, it has a tendency to give up one of these hydrogens, because the 3 plus is pulling so strongly in that, pulling the electrons into the center, that it makes it very easy to strip it off, and then you get a hydronium. So there's an appreciable amount of this. So whenever you have salts like iron trichloride or aluminum trifluoride, these are acidic salts as well. How do you calculate the pH? We're not going to, that's a little too complicated to get into here. The reaction equilibrium are a little more complicated, but you can know that, yeah, those salts are going to be acidic. So it's our summary of acidic and basic salts. So strong acids plus strong bases, those are neutral salts that completely disassociate. Example, sodium hydroxide reacting with hydrochloric acid, sodium chloride plus water. Weak acids plus strong bases, sodium hydroxide reacting with acetic acid to make sodium acetate. Well, we can compute the pH by looking at the pKb of the acetate ion, which is just going to be 14 minus the pKa of acetic acid, right? And so then we can just treat it as a base equilibrium problem. So strong acids plus weak bases, these are acidic salts. Example, hydrochloric acid plus ammonia to make ammonium chloride. That is an acidic salt. And we can compute the pH by calculating the pKa of ammonium by just looking at 14 minus pKb of ammonia. We were doing those in logarithmic form, right? That Ka times Kb is equal to Kw, but you could also think of it as taking the log. And if you take the log of both sides here, you get log of K plus log of Kb equals minus 14, or pKa plus pKb is equal to 14. So the sum of the pKa and this pKb of a conjugate acid-base pair is 14. Sometimes it's a little easier to work in logarithmic. Sometimes it's easier to work with the exponentials. Whatever it is, that works best for you. Okay. And then salts of small cations, acidic, but hard to calculate. We won't get into that. What about the weak acid, weak base salts? Well, the quantitative calculations are harder. You basically need to solve 2 equations simultaneously because you've got the concentration of the weak acid and the weak base. There's 2 of these equilibria fighting. You have to solve sets of equations simultaneously, and we're not going to deal with how to do that here. Yeah, we don't really have the mathematical tools yet. So which is stronger? This is what we can say. Well, a weak base plus a weaker acid, that should be basic, right? Because the acid is weaker, has less of affinity. A weak acid plus a weaker base, well, that's going to be acidic. So let's make this a little quantitative. Well, if you have a smaller Ka or Kb, that means a larger pKa, larger pKb, that would be a weaker acid base. So if Ka is greater than Kb, the solution will be acidic. If Kb is greater than Ka, the solution will be basic. So you just need to look at the Ks and Kbs and know at least in which direction it's going to go. Another way to think about it is bigger pKa, bigger pKb, weaker acid base. And those, again, those are the acid bases that combine to make the salt, not of the conjugate acid base pairs that are in the salt. So let's take an example. So caffeine is a base. It's a weak base with a Kb of 4.1 times 10 to the minus 4. Hydrofluoric acid is a Ka, as a weak acid with a Ka of 6.6 10 to the minus 4. So what would we imagine if we react with these? Don't drink that. you get out a salt, right? And the question is the salt acidic or basic? Well, the salt is going to be acidic because Ka is greater than Kb.